My goodness, it is 9 o'clock already. Time flies when you're having fun. Well, when you're writing emails, I guess, as in what I was doing this morning. All right. I do have just a few announcements before we take a look at 2.04. First, we'll let the audio catch up. There we go. All right. So hopefully you've seen the announcement posted in Canvas, but we are going to an Admirals game. Woohoo! So the high school staff, so me, Mrs. Cisneros, Mr. Doucette, we're all going to the Admirals game. That's on November 8th. We would love to have you join us there. Sign up though ends next week Friday, I believe. Tickets are only $6 a person, so it's not too bad. And it'll be a day of fun, right? So at least you get out of live classes for a day and get to enjoy some hockey. So I've only been to one hockey game before, and that was a college game, and I don't even think I lasted the whole time. So we'll see how this game goes for me on the 8th. But if you'd like to join us, we'd love to have you. Just don't forget to sign up before next week Friday. We can't have any late sign-ups because our tickets are numbered and the game is actually sold out. So make sure you sign up before next week if you plan on coming. All right. As far as the lessons go, we are throwing a lot of content into each of these lessons. So it's basically like an entire unit of Algebra 2 into one lesson in pre-calc here. So I know we ran out of time, or not really ran out of time, but ran long a little bit in Tuesday's class with lesson 2.03. So do you guys get a chance to look at that? Do you have any questions regarding lesson 2.03 at all? Okay, I know that we looked at like maximum, minimums, the IVT, stuff like that. Today, again, we have a lot in store for us. We're going to be looking at how to actually find the zeros of those polynomial functions. So we'll spend most of the time here reviewing how to find those zeros. And remember, there's a lot of steps with these higher degree polynomials and a lot of work that can go into it. So some of these can be a little bit tedious and time consuming, I guess is a better word for it, than some of the stuff we've seen in the past. All right, to start us off, the first thing we have to review is long division. Now, long division wasn't so bad when you were dealing with just integer values, but when we start throwing functions and polynomials out there, it's a little bit more tedious, right? But the process is still the same as if it were just integer values. When you're setting up your long division, I always look for missing terms in your polynomials and put zeros in as placeholders. If you can find and identify those missing terms before you start working through your problem, hopefully the confusion won't be as great and when you're working through and solving those. All right, now the whole reason for long division, and coming up here will be our synthetic division, is to see if a function, or if a zero, an integer is a zero of our function. There we go. Sorry about that, little tongue-tied. So that's the whole process behind this or not. Is there a remainder, essentially? That's what we're looking for. So is there a remainder? Because if there is, then that value we tested or that polynomial that we divided by is not a factor or not a zero of the longer function. So let's go ahead and just look at an example of how to do that long division, bring that back up to kind of the surface, so to speak. All right, we are dividing 2x to the fourth minus x cubed minus 2 by 2x squared plus x plus 1. So this is going to be on the outside here, so 2x squared plus x plus 1. Now, as I was writing this out, I was looking for any missing terms. I had degree 2, 1, none, so we are good there. Underneath my division sign, though, we're not as lucky, right? So as I start to write this polynomial, I have x to the fourth, x cubed. I do not have an x squared, so I'm going to put a 0x squared in. And I do not have an x, so I'm going to put a 0x in. So those are just zeros for the placeholder. So as I start to go through this long division process, when I get to the x squared and the x terms, I at least have space for it there and know that it's going to come up at some point through my long division process. All right, let's start it off and see what you can remember. We always start off out here by asking ourselves the question, 2x squared times what will give me a 2x to the fourth? And x squared, Rebecca says, to start off with. So I'm going to put an x squared down or up there, and I'm going to multiply through the divisor out here. So x squared times 2x squared is our 2x to the fourth. I have x squared times x, which is x cubed, and x squared times 1, which is x squared. Now keep in mind, I want this first term to cancel out that I have lined up. So I need to subtract or take the opposite of everything that I just wrote down there. I think that's the step that a lot of students forget, is making sure you're actually doing the opposite of those when you go to add them together now. So those cancel out. That's what we wanted to happen. We get a negative 2x cubed, a negative x squared, and I can bring down that next term of 0x. And then the process starts over. And now we ask ourselves, 2x squared times what is a negative 2x cubed? So what do we fill in next here? A negative x. All right, so that's going to give me a negative 2x cubed as I multiply through, a negative x squared, and a negative x. But remember, we want to do the opposite of all of these. So as I take the opposites there, that's gone. Hey, that's gone. I do have a 1x minus 2. And the minus 2 came from bringing down the term up from top. Now, as I get to this step, I now notice that the exponent on the outside is larger than the exponent underneath. When you get to that point, you have to stop, because this is now what we call the remainder. You can't multiply by anything. You can't multiply 2x squared by anything to get just your x anymore. So this is what we call our remainder. Because it's positive, we put a plus sign, and I have my x minus 2 all over whatever we divided by. So that 2x squared plus x plus 1 in this case. I want to ask for the polynomial in your fraction form. I believe this is what it's looking for, writing that remainder as a fraction. Okay, really good review of the long division process there. Questions with that? Okay, you guys did really, really well with remembering those steps. Usually that's a concept that we're foggy with, but you guys did a good job with that. Okay. Now the reason, correct, that is not, so that is not a 0 or not a factor of the polynomial. That is correct. So 2x squared plus x plus 1 is not a factor of that larger polynomial, 2x to the fourth and so on. That's exactly correct. We don't, luckily for us, we're not going to use long division too much with finding our zeros. We will use long division, though, when we have to locate asymptotes of our graphs. So that is going to come back and circle back at us again in an upcoming lesson when we're starting to talk about finding asymptotes and what these graphs actually look like. But luckily for us, we can use synthetic division and a couple other techniques that are a little bit faster than the long division process. We now have something called the remainder theorem and the factor theorem. And these two are basically the same thing. It's just depending on what your outcome is. So what these two theorems are stating is if you are given a factor, and you can work backwards to solve for x in here. So x minus 2 would give you an x equals 2 as a 0, right? So if I work backwards to solve for x in there and I substitute into the polynomial, I can figure out what the remainder is going to be. So that substitution is going to go a lot faster than the long division process, right? So let's go ahead in this first one here and actually substitute the value of 2 into this polynomial. All right, simplify that. Remember, you need to take exponents before you multiply, so make sure you're doing your 2 squared and then multiplying by 3. Don't do 6 squared there. Let me know what you get as a simplified answer. Rebecca got a 6 and Tommy got a 6. All right. Hopefully they're both correct or they're both wrong, but I'm going to go with the correct version there because that's what I got as well. Because you got an answer of 6 here, the factor theorem is stating that this is not a factor because it did not equal 0. Right? So because you did not get 0 here, this is not a factor of this polynomial, which means this is not a 0, 2 is not a 0, and 6 is what we would call the remainder. So if you were to do long division here, you would get 6 as a remainder at the very end. Okay, so a lot to kind of encompass there. So because we got an answer of 6, that's the remainder, which means x equals 2 is not a 0. It doesn't cross the x-axis at positive 2, which means x minus 2 is not a factor of that polynomial. So a lot of things to kind of piece together. All right, go ahead and try B and C then. So for B, we'd be testing x equals -1, right? Because when you take that factor, you'd want to subtract 1 from both sides. And in part C, you're actually substituting in a -4 because you have to subtract 4 from both sides to solve. So go ahead, take a moment, substitute those in. When you have the answer, go ahead, put it in the space provided. All right, looks like we got some answers popping up there. So part B, the remainder is -24, so that means that x equals 1 is not a 0, which means x plus 1 is not a factor. In part C, looks like you guys are getting 0 as your remainder, which is awesome news for x plus 4. It means x equaling -4 is a 0 of that polynomial, so the graph is actually going to cross your x-axis at -4, and it's the graph of this function right here. So that will cross at -4, which means that x plus 4 is a factor to that polynomial. Awesome. Any questions with the remainder and factor theorem? And again, they go kind of hand in hand. Now, the remainder and factor theorem will only work if you're dealing with a degree 1 for your factor. So that's why if you have anything higher than degree 1, you have to use that long division process. There's no other way around it. All right, let's go ahead and remind ourselves what that synthetic division process is, because we've used synthetic division in the past, and it helps us kind of speed up the process, but again, it only works if you're dividing by a polynomial that has degree 1. So again, we can only use synthetic division for dividing by something with degree 1. So let's take a look at an example here. Does anybody remember how to set up the synthetic division for a problem like this? It's been a while since we've seen it. How about what we put in the outer box? Let's start there. Anybody remember what's going to go in the outer box? A 3, right? It's your 0 that you're testing. So notice they give you the factor x minus 3. You always want to start your synthetic division out with the 0 of that. So you want to do the opposite, essentially. So it was a minus 3. We're putting a plus 3 in there. What do I fill my top row in with? So the top row is going to be filled in with numbers from where? The polynomial, yeah, this polynomial they give you. Now, I really stress putting zeros in for the missing terms in the long division. You must put zeros in for any missing term in synthetic division. If you don't, you will not get the correct answer. So this is a very crucial step here. So when I start pulling the coefficients on each term, if a term is missing, I need to put 0 in for that placeholder. I don't have any missing terms here though, right? Because it goes 3, 2, 1, none. So there's no missing terms in this example, but if there were, you have to put a 0 in. All right. Anybody remember now that I have my boxed number and the numbers for the top row, what we do from here? You got to bring the 2 down. Yep. So that first number is always going to be brought down. If you're below the line, you multiply with the box number. So below the line, we multiply 2 times 3 to get 6. Above the line, what do we do? So below we multiply. Above, not subtract, we add. Yeah, so above we add. Negative 3 plus 6 is a positive 3. Below the line, we multiply. 3 times 3 is 9. Above the line, we add. Below the line, we multiply. Above the line, we add. All right, now notice this last value here will always be your remainder. Now luckily for us, we had a remainder of 0. Yay! Which means that x equals 3 is a 0 of that polynomial, which means x minus 3 is a factor of that polynomial. We can go ahead and write the resulting equation that's left from these numbers 2, 3, and 4. So these values of 2, 3, and 4 do hold significance to the problem. And what they represent are the leading coefficients of the quadratic equation that's left over after the division process. So we always start with 1 degree less than what we began with. So because we started with a degree 3, we're now going to start with a degree 2. So degree 2, and then you count backwards from there. Degree 1, constant. So this synthetic division process is going to help us, hopefully, narrow down that polynomial so that we can get it to a quadratic equation. This is a quadratic equation in blue because it's degree 2. We know how to solve quadratic equations. We can try factoring, graphing, quadratic formula are the 3 main ones, right? So once we get it to this point, we can now solve for the other two zeros of that polynomial. Right, so that's the whole goal behind it all, is to get it down to, break it down to a quadratic equation so that we can solve using one of the methods that we know. All right, it didn't actually ask us to solve the rest of that. Are there any questions at all with how we got that blue polynomial? Correct. Yeah, so Isaiah says after we were to factor that or use a quadratic formula, whichever may be the case, I'm not sure if this actually will factor, to be honest with you. If it does, great. You would get your two remaining zeros that way, right? The third zero comes from up here, the 3. So x equals 3 is your third zero. That is absolutely correct. Good, because that's something we're always keeping an eye on, right? The degree tells us how many zeros there should be. Now we don't know if all the zeros are real or not, but it at least tells us how many there should be. All right, when we have the finding rational zeros here, we can use something called the rational zero theorem to narrow down our possibilities. Do you guys remember doing this in Algebra 2? So what the rational zero theorem basically allows us to do is create a list of positive and negative numbers that we can start testing using synthetic division. So instead of just randomly choosing values, it at least gives us some sort of a starting point to test things out. So to create that list of values, we do plus or minus P over Q. Hopefully this is going to bring back some memories. P are factors of your constant at the end. So in our case, that would be the 2 or negative 2. But because we're using plus or minus with these, the sign, it doesn't really matter. It's more the number that we're taking into consideration. So looking at that list, what are factors of positive 2? There's only 2 of them, right? 1 and 2. Yeah. Q are factors of your leading coefficient. What are factors of 3 in this case? And there's only 2 factors of 3, right? 1 and 3. Yeah. All right, so to create this list, it's going to get a little long. I'm going to do 1 over 1, 1 over 3, 2 over 1, and 2 over 3. Okay, well, it's not that long. At least this one wasn't that long. How many possibilities are there for us to test now out of that list that we just generated? How many possibilities are there? Or how many numbers do I actually have listed is what I'm asking. There's not just 4. There's more than 4. There's 8. Yep. Don't forget that there are actually 8 different values in this list. You do have the positives of all those numbers, and you have the negatives of all those numbers. So there are 8 possibilities that we should test, or gives us at least a starting point to test. After we have those possibilities, I would graph it and then take a look to see which ones are probably the best choices to start off with. So I threw the graph up there. Out of our list there, what numbers do you think would be good ones to test? So looking at the graph and where it might cross the x-axis, what numbers might be good to test? -2, yep, -2, +1, and then probably the -1/3 would be my guess. Maybe that's a -2/3. Looks more like it's a -1/3. I'm probably going to stick with one of the whole numbers though, or those integer values. Do we want to test -2 or +1? Which one do you guys want to test? -2. Okay. And technically, because we're starting with degree 3, we only have to test one of them until we get to a quadratic equation. So as I set up my synthetic division here, I'm looking for missing terms. And notice how I'm taking the signs of those leading coefficients. Okay. Below the line, you multiply. Above the line, you add. Below, multiply. Above, add. Below, multiply. Above, add. Woohoo! All right, so we got to the point where we have a quadratic equation. 3x squared minus 2x minus 1. So you can stop at that point and you can use either the quadratic formula or factoring if you'd like, or you can keep going. You can take this list here, and we said that +1 was another possible 0, or it looked like it was another possible 0. So you could technically set up your synthetic division using that answer and just continue on. So I bring my 3 down. I would start by multiplying, then you add, multiply, add. And 1 was also a 0 because the remainder was 0 there. So now I've done synthetic division twice, which means now I'm down to just degree 1, and I get a 3x minus 1. And you can solve that way as well for that last 0. So you could add 1, divide by 3, and subtract 1, divide by 3, because that was a +1 there, not a -1 when I did my math. And you get that third 0 of -1/3. So a couple different options there. You can continue with the synthetic division process, or technically you can stop after the pink one and try to factor and break down the polynomial that resulted there, which was a quadratic equation. All right, any questions with that process or anything of the sort? There are always many options, right, to try to solve a problem. That's kind of the nice thing, and maybe a drawback at the same time, right, because not everything is all black and white. There are some gray areas that you can take and can lead you into some trouble, I guess. But it always pulls you back. Yeah, exactly. There are limitations. All right. I do want to talk about upper and lower bounds because this is going to be addressed I believe, in the homework assignment. So as you're coming across and doing your synthetic division, the zeros that you're testing, they can have some significance to them. So like if I go back here, when I tested this value here and this value here, so -2 and +1, their answers had some significance to it. They are basically telling us, are there any zeros below that number, or are there any zeros above that number? So that is what we would call our upper and lower bounds. So as we're going through things and looking at what was left after the synthetic division, that can help determine if they have an upper or lower bound present. So here's how we can distinguish whether a value is an upper bound or if a value is a lower bound. It says if k is greater than or equal to 0, and every number in the last line is non-negative, so that's either a positive or a 0, k is an upper bound for the real zeros of f. So what that means is there's no value that's going to be larger than k that will work for you. All right? So if you find that, you can actually stop because nothing is going to work beyond that point. That's exactly correct, Isaiah. This is not to be confused with bounded graphs, right? Bounded means that the graph doesn't actually pass over that value. This is just showing you that a 0 doesn't go beyond that value. Not that the graph itself doesn't, but that there aren't any zeros present. The graph will not actually cross the x-axis after that point. So this is not testing whether the graph goes up above or beyond something or below. It's just whether the zeros will be present beyond or below. Now, as we are going through the synthetic division, so if all of the answers that you get are positive, we know that is bounded above, so there's no values that will lie above that number you tested. If your answers alternate signs, so positive, negative, positive, negative, positive, negative, that is a sign that it's bounded below. There are no values for k that will work below the one you tested. All right, it sounds really confusing, but once we put it into play, it's actually not that bad. So what they'll tell you to do is just test or prove that something is bounded. So it says, prove that all the zeros of this polynomial must lie in the interval of -2 to 5. So all you're doing is you're testing to show that -2 is a lower bound and +5 is an upper bound. So when you're doing the synthetic division here, for -2, your answers must alternate signs, and for +5, your answers must be all positive. That's essentially all you need to do to prove it. So let's start with the -2. Let's see if I can set up my polynomial here. All right, why don't you guys go ahead and run through the synthetic division, or someone take that one and run through the synthetic division on the board. And I'm going to set up the +5 right next to it, and then somebody can run through that one. All right, go ahead and throw the numbers in there to finish the synthetic division process. Awesome. So I'm just comparing to my notes, and both of those look really good. Notice in the -2 that your answers alternate signs. Positive, negative, positive, negative, positive. This is proof that -2 is a lower bound. Now notice that -2 is not a 0, right? It just means that there will be no zeros after that point. Okay, so -2 is not a 0 itself, but it's kind of a cutoff point because you're not going to find any zeros lower than that. All right, +5 on the other hand, all of your answers here are positive, 2, 3, 7, 49, 2, 53. +5 is not a 0 itself either, but it does show an upper bound. So that means that it's not worth testing any number larger than 5 as a 0 because it's not going to work. So 5 is telling you, nope, nothing above here is going to work. So if you have anything larger in your list, like that list we created, P over Q, throw it out because it's not going to work. Okay, so that's essentially what your upper and lower bounds would do for you. Honestly, we don't look at upper and lower bounds too much. They don't play too much significance with our finding zeros process, but it can be beneficial if we are on the lookout for them every once in a while. And you'll definitely have to prove that something is a lower or upper bound, so that's just using your synthetic division process to do so. One of the rules that we learned back in Algebra 2 was Descartes' rule of signs. We will not be going over Descartes' rule of signs, but it does, again, give you another piece of information to help you narrow down the choices. So what this rule of signs says, you can determine how many positive, negative, or complex zeros a polynomial possibly has. We are not going to focus on that. I don't believe it comes up in your homework, so but just note that there is that rule out there to help you narrow down your choices even more if you need it. All right, let's go ahead and we got a few moments left of class here to practice. So let's set up some Let's set up some synthetic division. When I set up the synthetic division, what number is going to go in my boxed area? 10 goes in the box area. Good. And again, it's synthetic division works here because we're dividing by degree 1. If we were dividing by anything that's larger than degree 1, it doesn't work. All right, what numbers do I fill in my top row? Be careful. What numbers do I want to use to fill in the top row? Yeah, we got to throw 0 in at the end. So 9, 7, negative 3, and 0. The 0 is signaling your constant, right? You need to have a constant or degree 0 at the end. If you don't put it there, you're not going to get the correct answer. All right, go ahead, fly through that synthetic division. Let's see what we get as a result. All right, yeah, it looks like 9,670. Let's throw that. I'm going to throw this as a remainder up there. I think Rebecca might still be working, not sure. But yeah, that synthetic process looks good. All right, it does say to write a summary statement in fraction form. So how would we write this resulting polynomial then? Or what is the resulting polynomial from dividing by x minus 10? All right, yeah, not pretty, right? Notice how Tommy started with the 9x squared. 2 is 1 less than your starting degree, which was 3, plus 97x plus 967 plus 9,670, all divided by x minus. Instead of doing the long polynomial, do what you divided by x minus 10. Yeah, so that shortens it a little bit at least. Not by much, but a little bit. It's not quite, no, it's still ugly. All right, questions with writing that answer in fraction form there? All right. It says use the remainder theorem to find the remainder. All right, so remember the remainder theorem is just using substitution. Go ahead and substitute the value in, and when you have the remainder, throw it up on the board. We got one answer of negative 43. Did anybody else get that same thing or anything different? Oh, there's two answers. All right, I would agree with that answer. We should get a negative 43. So what does that answer of negative 43 mean? Means negative 3 is not a 0 to our function that's listed. Yep. What else does it mean? So if negative 3 is not a 0, what else is not happening? What's not a factor? So x equaling negative 3 is not a 0. What's not a factor of the polynomial then? X plus 3. X plus 3 is not a factor to the polynomial. Good. It says use the factor theorem to determine whether the first polynomial is a factor of the second. All right, so they give you a factor here of x minus 2. Using the factor theorem means substitution. So what exactly are you substituting into the polynomial that's listed behind there? So we want to test, yeah, you need to solve for x, right? You should be only plugging in zeros into your polynomials. So you want to add 2 to both sides and then substitute in. So now substitute real fast. What does that simplify to after the substitution? An 8. Okay, if it equals an 8, is x minus 2 a factor to x cubed plus 3x minus 4? No, because x equals 2 is not a 0, which means x minus 2 is not a factor. Good. 10. I got 10 too. Let's recheck the substitution. We came away with the same answer, but I also got a 10 now that you say it. Now that you said that. 2 cubed is 8 plus 3 times 2 is 6 minus 4. So that is 14 minus 4 is a 10. Yeah. So it doesn't change the answer at all, but we probably should make that a 10. All right, no worries there. Let's see. We won't have time to go through this, but what would we do to prove that k is an upper bound or k is a lower bound? So what do we do? What's the process? You need to use synthetic division. Now when you're setting up synthetic division, look for missing terms. That's the key thing. All right, once you have your answer, what are you looking for a upper bound? So an upper bound, what are you looking for in your answer? All positive numbers under the line. Yep, so all positive numbers under the line. In a lower bound, what are you looking for? Alternating signs. Yep, so you're looking for alternating signs, whether it's negative positive or positive negative. They've got to keep flipping back and forth. Good. So we won't have time to run through those two here today, but I think you can handle those on your own. You guys got the process down and know what you're looking for. All right, you should be good to go for the 2.04 lesson. Any major questions that stand out to you guys with that? All right, you got a really good head start on it, so I'll let you go so you can work on it. If you do have questions that come up, remember I do have office hours today and tomorrow, so don't hesitate to come in and see me or send me an email. Other than that, I'll let you go. Have a great rest of your week and a great weekend, and I'll see you guys all again Tuesday. Bye, everyone.